This is week 4, screencast 1, 571. And the title of this week is Basic Control Charts Part 2. Last week, I brought up the idea of using probability limits to find the limits for a S-chart, standard deviations chart. And in computing these limits, you need to have the ability to compute chi-squared quantiles. So how do you get chi-squared quantiles? I had a lecture question which asked you to find a specific quantile, and I kind of let you work on that on your own. But there are a couple of options that you have. You can use software or approximations. I am sure there's some web calculators out there that will give you chi-squared quantiles for arbitrary probabilities and any number of degrees of freedom. There are very good calculators that have the chi-squared CDF and quantile function programmed in them, and in my opinion the best business calculator is the HP30B, and it has all necessary functions for that, and it's pretty cheap. It's 15 bucks, I think, Amazon. It has the Black-Scholes formula for pricing derivatives, programmed by some guys in New Zealand, and they just gave it to HP, and HP put it into the firmware of the HP 30B calculator. But the HP is just a well-designed system that has just a whole bunch of business relevant computations, a lot of finance in it. But it's instructive to look at approximations. And in my on the online system, I have an approximation due to some work by a guy named Czar in 1978, and here's how it goes. I'll move this over to the other screen so it doesn't get in the way. So let's say you want to approximate the chi-squared with new degrees of freedom at the probability alpha. So this, by the way, is this is the chi-squared with new degrees of freedom, and this is the value alpha, the alpha right here. So you want to find this quantile, and that's right, and that's this value right here. So this turns out to be equal to z squared 1 minus alpha over 2 for nu equaling 1 degree of freedom. And the interpretation is that you have an upper tail value, z-score, z sub alpha, and you always take the area to be in the upper tail when you see this notation z sub alpha. It's a special notation reserved just for the standard normal distribution. Notice that down here the area is below the quantile value, but this is not a quantile. This is the point. You can view this as the quantile at the point 1 minus alpha, at the argument 1 minus alpha. So this notation, you would draw this picture. This area is 1 minus alpha over 2 because it's the value in the subscript. Well, if you have 2 degrees of freedom, you would compute the logarithm, the natural log of the value 1 minus alpha, and multiply it by -2, and you would get the quantile, the alpha quantile, exactly. But if you have more than that number of degrees of freedom, then you have to compute this long-winded approximation, which actually works pretty darn well for even small degrees of freedom, and then it works really well as the degrees of freedom gets bigger. But as you can see, you've got to kind of punch away on your calculator to get the whole thing computed. But there's no rocket science to it. The trick is that you understand what this z alpha notation is. And then you just plug and chug the rest of the formula and you have yourself an approximation. So it's approximation because I put a little squiggly guy here on the equal sign. And so, like I say, this is computed for my. This is discussed in my tutorial. And for example, for nu equals 5, the third equation gives chi-squared 5.05 equaling 1.12799. You might want to check or verify. And again, you say, oh, that's annoying, I'm not going to do that. Well, when it comes to exams, I'm expecting computational skill. So here's a baby problem where you know the answer. Find a calculator and crank it out. Z sub alpha is, in this problem, is 1.645. So it's good to have a quick mental image of what these two distributions are looking like. over here is 0.05, and over here is 0.05. See they're opposites. In a like manner, the 0.95 quantile is approximately 11.044. Z alpha in this case is negative 1.645. So this approximation formula is really freeing because it says that it doesn't matter what false positive rate you're thrown or how big your subgroup size is. So in this example, 5 would be the subgroup size, n minus 1, so the subgroup size must be 6. I recommend that you buy a calculator so that you can, and then read the instruction booklet and figure out exactly what buttons to push to get the quantiles. But if you don't want to do that or you can't, then this approximation formula can be worked out on any calculator that has a log button, an ln button. So we come to a management relevant question. When did the mean shift? So this is after an X bar chart gave signal. So you got your X bar chart, and you got your 2 control limits, and you're monitoring X bar by subgroup, and everything's going along just fine when boom, you get signal at this point right here. So you pull the master switch on the production line and all the machines wind down and everybody looks at you. Well, now what? And you say, well, okay, first job is we've got to find out why the mean shifted on our production process of this critical metric, critical dimension that we're keeping track of. And so you hunt around and you finally find it. And then you crank the line back up and everybody gets back to work. But you get called into an office by some high-level manager, and they say, well, you taught us that system that you got there, that control chart business, is going to squeal when the mean shifts. Yeah, that's what control charts are for. And this senior person says, well, doesn't that beg the question, how long have we been operating in a state of being in a fool's paradise, in that we've been thinking everything's cool, and all along the mean has shifted, and finally our chart got around to saying, hey, I think the mean has shifted. Do we need to go back no groups? Did it shift right on that subgroup? Or did it take a little while for the chart to detect a problem? And if it took a little while, how many parts, how many units have we made and put in boxes and shipped off to customers that were made with a different mean? Maybe some of those parts are no good. And even if they aren't good, maybe they're not quite as high performance as when we had everything in control, and maybe we should recall those units and rework them. Let's say you're providing some sort of avionics to the aircraft, or say the military, and you've got certain voltages that you are keeping tight controls on your circuit boards. And one of those voltages is your control chart. And you've been testing automatically this critical voltage. And you know that when the voltage shifts, that means something else on that circuit board has changed. And that means trouble. That means all those circuit boards for which the chart now says were made under a different average voltage, all those circuit boards should be thoroughly tested component by component. Well, they're installed in aircraft. So you really need to put out a memo saying, take the board out of the avionics and ship it back to us. So senior management says, seems to us we got to know the point at which we had a shift. And this is cleverly denoted in Ryan as T with the word shift as a subscript. Because all the parts that we made from here to here, all these units, we might have to recall them. Well, if we're going to do a recall, that's going to be expensive, and it's going to mess with our customer opinion of us. So we don't want to be recalling too many, and we certainly don't want to be where we don't recall enough. So we need to ask you, as our quality analyst, an important question. How far back in our serial numbers should we issue recall notices? This is a pretty important problem, and a company can get sunk if they don't handle it in a way that's accurate. So they're looking at you and saying, please tell us when you think the process shifted its mean on us, given that we have signal. Well, if you've taken some point-and-click quality course, you're going to be just dumbfounded. You won't have any intelligent response. But luckily for you, you're taking a course based on Ryan's book, because on page 116, he's got a way to estimate T-shift. So this is not an academic issue. This is why this course is inside a business school, because this is going to affect the bottom line of the company and also customer perceptions of your firm, which will impact your ability to acquire new business. So Ryan says, okay, you observe stage 2 subgroups. At time points T1, T2, up to Tn0, which Ryan calls uppercase T. And this is the time of signal. So on the subgroup that was taken at time uppercase T, that subgroup's mean fell outside the control limits. So the process shifted at some point one step back or more from uppercase T, which we're calling T sub n0. Okay, because you're in stage 2, you know that you were in control at the beginning of stage 2. So here's T1, here is stage 1. See, the cool thing about control charts, it's important to re-emphasize, is that because of the way control charts must be built, that is, you have to establish control of the process in stage 1 before you're allowed to go into stage 2. Because of that, you have one point at which you know things were okay, and that is the point just before you started stage 2, because you made sure that up through stage 1 that you were in control. But things could have gone bad on the first subgroup in stage 2, unbeknownst to you. So you monitor along, and at Tn0, that's when things went bad, and you got signal. So here's the upper control limit, and here's the lower control limit. And so you say got up there, or you got down there. You're mean. So maybe you shifted here. Who knows? You've got to come up with some estimate of when you shifted. So we're going to put a little hat on top of the T, and we're going to say T shift hat. So that's an estimate of when we shifted. And notice I've drawn them at different places, because there's no guarantee that your little estimate is going to come dead on, right on the point at which, the true time point at which you experienced a mean shift. The best you can do is estimate it. So what are we going to compute to get this estimate? Well, we've got to do a little bit of computer work. This is not something that has a closed form, something that you can just tap in your calculator once and out comes the estimate. You've got to do a couple of computations, and probably you'll want to program this in your quality improvement software system. I'm advocating the use of SAS, but when you get out in the big bad world and you get a real job, who knows what software you will be told to use. Or, in a lot of situations, it will be up to you, and like I was talking to somebody last week who's working at a big firm in town, because they're experiencing some financial hardships, they just said, we're not buying anybody any software, period. So you're kind of on your own all of a sudden. But, of course, you still have to keep the company in a state of high quality. That is unquestioned. It's just that you've been given no resources. Well, you know, welcome to the real world. That's the way it is. So you've got to work with what you have available. But whatever you do, and I don't care how you do it, you've got to make this computation right here in order to give the best answer as to how far back in production you need to go with your recall memos, recall letters, recall emails. So here's the setup, and this is in this is in Ryan. This is the word argument, and this is the word maximum, and the two strung together is pronounced argmax, and it's standard mathematical notation. And argmax says this is a test function. Every function has an argument, i.e. the value that goes into the function, and out comes the function value. So you read this as follows. T is a member of the set T1 or T2 or T3 up to T sub n minus 1, n naught minus 1. Take sequentially each T value, T1 first and then T2, stick it into the formula here and here, and compute the value of the test function. Set the value aside. Put in the next value of T from this list. Compute the function, the test function. Put the value to one side. And then sweep your eye down all these values, these function values, and find the one that's the biggest, the max. Look at the t that's responsible for that function value and return it as your estimate of t shift. And I'll continue this in the next screencast.